This video is not intended to teach you any new theory. It's just meant to help you with your final revision and exam practice as you prepare for the exam. We're going to be looking at 3 questions taken from recent paper 2s and focusing just today on force and motion. If you'd like to download or print these questions before we start, there's a link below so that you can do that. Okay, so this first bit. State the principle of conservation of momentum. It's a very common question, of course, but it's also one where it's very easy to score 0 marks even though you think you've written a good answer. So for example, if you say the momentum before the collision is equal to the momentum after a collision, that will score you 0 because you've missed the 2 key facts. The first one is that we're talking about the total momentum. So you can say total momentum before a collision is equal to total momentum after a collision. Or you can say total momentum is conserved, which is quicker. And the other key point that you must mention is if no external force acts. And the other way to say that is to say in an isolated system. So the total is important, or the sum, you could say the sum of the different momentums before a collision is equal to the sum of the different momenta after. But you must mention either sum or total, and you must mention the condition of no external force or an isolated system. Okay, so now we've got a calculation question to do on momentum. A stationary firework explodes into 3 different fragments that move in a horizontal plane as illustrated. And we can see there the 3 pieces. Stationary tells us that the total momentum beforehand was 0. And therefore we know that the total momentum afterwards also has to be 0 because momentum is conserved. And what this question asks us to do is to use the principle of conservation of momentum to determine theta, the angle there that you can see marked for 2 of those fragments. So what I'm going to do is I'm going to look at the momentum in just what appears to be there, the vertical direction. And we can see that one of those particles, one of those objects is moving upwards and the other 2 are moving downwards. So their vertical momenta must cancel out. They must be equal. The 2 at the bottom must be equal and opposite to the 1 at the top. So let's try it. Upwards, we've got a momentum mass times velocity of 3m times 7. I'm going to leave out the m because it will appear in each bit of the equation and therefore we could cancel it out. And that must equal the sum of the other 2 vertical ones. Now, because these 2 are not actually moving in a vertical direction, we're going to have to take components here. So let's start with the vertical component of this one. Now you can see if I draw that right angle triangle there, that the vertical component is opposite that angle. If it's opposite, we're going to use sine. So 6 sine theta is the component we want there. And similarly on the other side, that wasn't very straight, it's going to be 8 sine theta there. So what have we got then? For the one on the left, we've got 2m times 6 sine theta. And for the other one, we've got 1.5 times 8 sine theta. So 3 times 7 is 21, 2 times 6 is 12 sine theta. 1.5 times 8 is also 12 sine theta. So what we've got is that 21 equals 24 sine theta. And rearranging that gives us sine theta as 21 over 24, which will give you 0.875. And if you do shift sine on that, you will get 61 degrees. Okay, the next part asks us to work out a ratio of kinetic energies, which is really a straightforward thing to do. Kinetic energy, we know we can find using half mv squared. So if we do that for those two pieces and find the ratio of them. So on the top, the 2m mass, half times the mass, which is 2, and the speed of that one was 6. And on the bottom, half times the mass, 1.5, times the speed squared, which was 8 squared. So half and 2 cancel out, and we've got 36 on the top. 8 squared is 64 times 1.5 times a half will give us 48, which gives us a ratio of 0.75. This one, we're going to have to read some data from a graph for this. So let's see what the situation is first. A child on a sledge slides down a steep hill and then travels in a straight line up an ice-covered slope. The sledge passes point A with speed 18 meters per second at time t equals 0 and comes to rest at point B. The child applies a brake, but the brake does not keep the sledge stationary and it immediately slides back down the slope towards A. So what we've got is this child is starting at A at 0 seconds, sliding up the slope, reaching B, and then starting to slide back down again. Let's have a look at the graph, what it tells us. Well, you can see here at t equals 0, we start at 18 meters per second, and the speed gradually decreases to 0 at 12 seconds when it stops momentarily at B. And then the speed starts to increase again, but in a negative direction as it slides back down the slope towards B. Okay, the first part we're asked is the time taken for the sledge to travel from A to B. Well, B is where it stops momentarily, where the speed reaches 0, so it's this 12 seconds here. Determine the displacement of the sledge up the slope from the point A at t equals 24 seconds. Let's go back to the graph and see what we can work out. If we look at the area under this triangle here, that will tell us how far she went sliding from A to B. So it will tell us the distance from A to B. So let's work out this area then. Half base times height for a triangle is half of 12 times 18. And that will give you 108 meters. So it's 108 meters from A to B. And then this triangle here will tell us how far she slid back down again. So again, we're going to do area half base times height. The base from 12 to 24 is 12 seconds again. But this time, if you notice, the speed there stops at 6 or negative 6. So half of 12 times 6 will give us 36 meters. So from A, she first slides up 108 meters and then she slides back 36 meters. So we'll need to find the difference between those. So I'm going to put here from graph so that we don't have to do all of this working again. She slid 108 meters up and 36 back. The difference there is 72 meters. So that's how far she is from A now. In C, show that the acceleration of the sledge as it moves back from B back towards A is 0.5 meters per second squared. Again, we can take this data from the graph, and I'm going to take data to put into this equation. So from the sliding back from B, I want to know what the initial, the final speeds are and how long it takes. So let's go back to that graph. Well, the initial speed is 0. The final is 6 or -6 here. And the time taken is 12. So what did we say? Our final speed is 6. Our initial speed was 0. Time taken is 12, which does indeed give 0.5 meters per second squared. In D, we're told that the child and the sledge have a total mass of 70 kilograms. The component of the total weight of the child and the sledge that acts down the slope, that is along the slope, parallel to the slope, is 80 newtons. We have to determine first the frictional force on the sledge as it moves from B towards A. This is a fairly common style of question as well, which is really looking at Newton's second law, in that the resultant force is equal to mass times acceleration. Now, you wouldn't need to write that down. That's just to explain what we're doing here. The resultant force acting on this child, well, if you imagine there's the slope, and I'm not going to attempt to draw a girl in a sledge. That's just represented by that box there. We know we've got 80 newtons acting down the slope, which is the component of her weight down the slope. And if she's sliding down, there must be a frictional force acting upwards like that. And the resultant of those will give us the mass times the acceleration. So if we look at the resultant of those, it's going to be 80 minus F, little f for friction there. The mass, 70. And we know from the last part of the question that the acceleration is 0.5. So in other words, 80 minus the frictional force equals 35. So the frictional force will be 80 minus 35, which gives us 45 newtons. Next, we have to work out the angle of the slope to the horizontal. So if we just have a look at this diagram again, we're taking this angle here, theta. Now, her weight is actually acting vertically down. That's the mg. And the component of that weight along the slope is mg times theta, sine theta. Now, you can work that out by looking at right-angled triangles in there, but I find it quite difficult to see the angles clearly when the directions I want are not horizontal and vertical. So I prefer to learn this one, that the component of the weight acting down a slope is always mg times the sine of theta, when theta is the angle of the slope to the horizontal. So what do we know then? We know that 80 newtons is equal to her mg sine theta. So we know that 80 is equal to her m is 70, g is 9.81 times sine theta. So if we work that through, 70 times 9.81 gives us 686.7 sine theta. So sine theta is 80 divided by that. Which gives me 0.1165. And then if you do your inverse sine on there, that will give you 6.7 degrees. Part E, the child on the sledge blows a whistle between t=4 and t=8 seconds. The whistle emits sound of frequency 900 Hz. The speed of the sound in air is 350 meters per second. A man standing at point A hears the sound, and we have to use the graph to work out the initial frequency of the sound heard by the man. Well, this clearly is about the Doppler effect. It's part of the waves topic, but it's often tagged on to the end of a question like this where objects are moving. So the equation you have on your data sheet is FO, which is the observed frequency, the frequency that the man will hear, equals Fs, the frequency of the source, the frequency that's actually emitted by the whistle, multiplied by the speed of the sound divided by the speed of sound plus or minus the speed of the source, the speed that the girl's moving at. Now, you have to remember when to use a plus and when to use a minus. You use a plus when the objects are moving towards each other. You use a minus when they're moving apart. Now, if you find that difficult to remember, I do. So I try to work it out in each case. I know that if an object is coming towards me, if a car is coming towards me, I hear the frequency increase. I hear a higher frequency, and the frequency is lower as it moves away from me. So when an object is moving towards you, you hear a higher frequency. Let's think about how this works with the fraction. If you're going to hear a higher frequency than it's actually emitting, you need this fraction to be bigger than 1, which means you need the number on the bottom to be smaller than the number on the top, and therefore you need a negative here. So that's how I remember it. Moving towards, you use a negative. Moving away, you use the positive. So let's do it anyway. So the actual frequency is 900. The speed of sound is 340. And the speed of sound plus Vs, well, this is where we need the graph because we need to see what speed she's going at 4 seconds. Why 4 seconds? Because it says the initial frequency heard by the man. So what does he hear at 4 seconds? So let's just go up and see what speed she was going at 4 seconds. 4 seconds is here. That's 12 meters per second there. So let's put that down here. So that is actually 900 times 340 over 352. So if you've got a calculator handy, you can try that and you will get 869 Hertz. Or you could round that to 2 significant figures and make it 870. Part 3 there, describe and explain qualitatively. Qualitatively means we don't need to use any numbers. The variation, if any, in the frequency of the sound heard by the man. Well, if you think about that graph, the girl was decelerating between 4 and 8 seconds. So if she's decelerating, then the Doppler effect is going to decrease because it depends on the speed of relative movement. So you can think of this in 2 ways. You can either think of it in terms of physics and say if her speed is decreasing, then the difference between the observed frequency and the source frequency will decrease. She'll hear closer and closer to the 900. Or you can think about it mathematically and think what happens as this number 12 decreases. What does that do to the fraction? But I'm just going to say here, the frequency of the sound increases because her speed decreases. Okay. This next one is looking at writing down expressions with no numbers, with symbols rather than no numbers. And usually these questions involve putting together expressions that you know and combining them to come up with new ones. So let's have a look. We've got a resultant force moves an object of mass m through distance s in a straight line. The force gives the object an acceleration a so that its speed changes from the initial speed u to final speed v. And we have to first write an expression for the work done by the force in terms of a, m and s. Well, we know that work is force times the distance moved in the direction of the force, which in our case is s. But we have to give this in terms of a, m and s, not f and s. So we're going to have to use the fact that f equals ma to rewrite this. So instead of writing f, we'll write ma times s. So there's our work done. Part 2, the distance in terms of a, u and v. Well, this one is like one of your equations of motion. You've got an equation of motion that looks like that. And if you rearrange that, you get, we'll do it in steps. And then to get s on its own, we would just divide both sides by 2a. So we get s equals v squared minus u squared divided by 2a. Then the next part asks us to put these together to find this expression for kinetic energy, and we have to explain the work in here. So what we're going to do is we're going to take this equation for W, for the work done, and we're going to say that the work done is equal to the increase in kinetic energy. As a force does work on an object, it's accelerating it, it's giving it kinetic energy, and the work done and the kinetic energy gained will be equal. So we're going to make our kinetic energy equal to W, which is equal to MAS. And then we're going to substitute in for that S, the expression that we got below here. The explain is where we say work done equals the kinetic energy gained. That's where we justify what we're doing. So kinetic energy then is the MAS, but we're going to substitute in, instead of S, that thing there, v squared minus u squared over 2a. So the a's will disappear, and it's starting to look a bit like kinetic energy now. We've got the half, we've got the m, and we've got the v squared. Yeah. And if you're wondering, why is that different from our usual half mv squared? Well, we've got a change in kinetic energy here. Remember, the kinetic energy is increasing, so half m times u squared would be the initial kinetic energy. Half m times v squared would be the final kinetic energy after the acceleration. And using that bracket there with the v squared minus u squared gives us the difference between them. It's the gain in kinetic energy. Okay, in B, we have a ball of mass 0.040 kilograms projected into the air from horizontal ground, as shown. It's launched from a point X with a kinetic energy of 4.5 joules. And at point Y, it has a speed of 9.5 meters per second. We're going to ignore air resistance. Okay, let's see what we're going to be asked to do here. We're probably going to have to come back to this diagram in a second. For the movement of the ball from X to Y, draw a solid line to show the distance moved and then the displacement moved. Okay, so this is asking you, do you know the difference between distance and displacement? Now, the distance moved will just follow the path of the ball. So that there is our D. And our displacement then is just a straight line, S. Yep. Okay. Then, by consideration of energy transfer, determine the height h of point Y above the ground. Okay, so what we've got here, let's have another look at the diagram. We are starting off at point X with a certain amount of kinetic energy, 4.5 joules of kinetic energy. As the ball rises, some of that kinetic energy is going to be turned into gravitational potential energy. But we're still left with some kinetic energy at point Y. It hasn't all been transferred because we've still got a speed of 9.5 meters per second. So we're going to use conservation of energy here and energy transfer. We're going to say that that initial 4.5 joules of energy becomes the kinetic energy at Y plus the gravitational potential energy at Y. Yep. So this is like our initial energy and our final energy. They are conserved. So let's see what we've got then. 4.5 joules, kinetic energy half mv squared. The mass of the ball was 0.04 and the speed at Y, we are told, is 9.5 meters per second. The gravitational potential energy will be mgh, so 0.04 times 9.81 times by h. So let's see what we've got here. Right, 9.5 squared. I get here. And on this side, okay, let's do a little bit of rearranging here. Okay, so that gives us here 2.7. So h then will be 2.7 divided by that 0.392. And that gives me 6.9 meters for h. In the last part, we have to sketch the variation of kinetic energy of the ball with its vertical height. We've said that the kinetic energy is going to decrease as it rises because it's being transferred to gravitational potential energy. And now we have to show what that looks like on a graph. A graph of kinetic energy against h. It says numerical values are not required, but it might actually be useful to think of those. I find it helps to think of them. We know that when the height is 0, the kinetic energy is 4.5. And we know that when it gets to h, the kinetic energy is still 1.8. We don't need those numerical numbers, but I find they help me. What we need to do is to decide whether this line is going to be straight or curved, and if it's curved, how it's curving. So what I'm going to do is repeat the equation we had just above there, which said that 4.5 joules is turned into kinetic energy plus mgh And I'm going to rearrange this equation to make it look like this. Because what I'm trying to do is to see whether it fits y equals mx plus c. Oops. And in order for me to do that, it may sound silly, but I like to change this around so that I've got the pieces in the right order, so that it really does look like y equals mx plus c and not like y equals c plus mx. So what I'm going to do here is just check okay, so the y-axis is our kinetic energy, the x-axis is our height, and we do have a constant in front of it. The mass doesn't change, a g doesn't change, and therefore this is a straight line graph. So what we're going to do then is just draw a straight line from here to here, and there we have it. I hope you found that helpful. If you have any questions, feel free to add them in the comments below the video and I'll do my best to respond. You will also find below this video a link to some more questions similar to these which you can try on your own if you want to. Good luck.